Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 5, which is all about gases. Now, understanding the physical properties of gases, especially focusing on the relationship between variables like pressure, volume, and temperature, are going to allow us to be able to answer some really important questions like, why does the pressure of a gas increase when it's compressed? Or why does a gas expand when heated? Also, why does a gas diffuse through a room? We're going to try to answer these questions as we go through this chapter. And that means we're going to have to cover the following objectives. Objective 1, we're going to define pressure. We're going to define pressure and we're going to discuss units of pressure and also talk about instruments that measure pressure. Then we will begin a discussion on the gas laws. Here we're going to cover Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law as well. Then we're going to use our knowledge of the simple gas laws and express them in a way that shows the relationship between volume, pressure, temperature, and number of moles. Essentially, what we're doing in the third objective is building up to the ideal gas law. Then our fourth objective is on gas stoichiometry. Here we're going to expand our stoichiometry toolbox and learn about liter-to-liter ratios as well as STP, standard temperature and pressure. Our next discussion is then going to be on Dalton's law of partial pressures. Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the sum of the individual partial pressures of each gas. We're going to explore some important formulations here, and we're also going to work through this definition conceptually as well. Then we're going to discuss the kinetic molecular theory, which shows how the macroscopic properties of gases result from the behavior of the individual particles making up that gas. Then our seventh objective is going to be focused on understanding the difference between effusion and diffusion. And then last, but certainly not least, we're going to briefly discuss real gas laws and how they differ from the assumptions we make dealing with ideal gases. We're going to cover a lot of really important and very interesting topics in this chapter, so let's go ahead and get started with the first objective titled pressure. Now, this objective is definitely focused on pressure, but I also want to define temperature and volume very briefly. We will get more elaborate definitions, especially for temperature, in a later chapter, but I still want to introduce it here. Temperature, this is defined as a physical quantity that expresses hot and cold. Or in other words, it is a measure of the average kinetic energy of atoms or molecules in the system. Now, volume, this is defined as a scalar quantity expressing the amount of 3D space enclosed by a closed surface. Now, pressure is defined as a measure of the force applied over a unit area. Okay, let's think about what that means. And to do that, well, let's talk about gases. A gas uniformly fills any container. It's also easily compressed, and it mixes completely with any other gas. One of the most obvious properties of a gas, then, is that it exerts pressure on its surroundings. So, for example, when you blow up a balloon, the air inside, it pushes against the elastic sides of the balloon and it keeps it firm. And so, from that, we know that gas exerts pressure on its surrounding. And this definition can be expressed mathematically as force divided by area. Force divided by area. Now, for a given force, the smaller the area over which that force is exerted, the higher the pressure. Now, the SI unit for pressure is pascals, which is also equal to newtons per meter squared. In other words, 1 pascal represents 1 newton of force exerted over 1 square meter of area. Now, what's also important to note is that we're going to encounter different units of pressure, and we're going to need to be comfortable and knowledgeable about how to convert between different units of pressure. Common units of pressure that we're going to encounter is Pascal, bar, millimeters of mercury, torr, all right? These are all, and the atmosphere. These are all really important units. 1 atmosphere is equal to 101,325 pascals. It is also equal to 1.01325 bar. 1 atmosphere is also equal to 760 millimeters of mercury, and it's equal to 760 torr. 1 torr is equal to 1 millimeter of mercury. Please spend some time familiarizing yourself with these units. Commit some to memory. It'll definitely be worthwhile. We're also going to tackle many different kinds of problems that are going to help us practice. But now the next thing we want to cover is, well, how do we measure pressure? There are 2 instruments that we want to discuss that measure pressure. The first one is the manometer. This is an instrument that's used to measure the pressure of a gas in a closed container. And one type consists of a gas attached to a glass U-tube that is open for the atmosphere, open to the atmosphere. Now, this tube is partially filled with liquid mercury, and the mercury responds to the pressure exerted by a gas in the container on one side and to the atmosphere on the other. Now, the second kind of instrument that measures pressure is the barometer. The barometer is used for measuring atmospheric pressure, and it consists of a long tube that is closed at one end and filled with mercury. Now, thinking about this, the weight of the mercury column inside the tube, it creates a downward force due to gravity. And that is balanced by the atmospheric pressure that's pushing on the reservoir. All right. If the atmospheric pressure increases, it's going to push more mercury up into the tube. And if the pressure decreases, then the mercury level is going to drop. So it is a balancing force act here. The height of the mercury column in the tube is going to be measured, usually in millimeters, and the height corresponds to the atmospheric pressure. All right, so these are the 2 instruments that we're going to cover here. What we want to do next to kind of solidify this objective is do a couple of practice problems that help us do some pressure unit conversions. This problem says, the pressure of a certain gas is 1.75 atmosphere. Express this in the following units: millimeters of mercury, torr, and pascal. Okay, great. Let's go ahead and do that, starting with A. All right, what we have is, we're told we have 1.75 atmospheres, and we want our answer in units of millimeters of mercury. So we need to find a conversion from atmospheres to millimeters of mercury. Let's go back to our table and remind ourselves what the conversion factor is. 1 atmosphere is equal to 760 millimeters of mercury. All right, we're going to use that conversion. All right, we're going to put atmosphere in the denominator so the units cancel out. And we're going to put 760 millimeters of mercury in the numerator. Notice that atmospheres cancel out, and then we can just plug this into a calculator. We're going to get 1,330. All right, so 1.7 atmospheres is equal to 1,330 millimeters of mercury. Now, part B, we want it in units of torr. There's 2 ways we can do this. We can start off by saying we have 1.75 atmospheres, and then we can find the conversion factor between atmospheres and torr. 1 atmosphere is equal to 760 torr. All right, and that's going to give us 1,330 torr. Something else that you could have caught on is that, well, we know that 1 millimeter of mercury is equal to 1 torr. So if we calculated the units in millimeters of mercury to be 1,330, that's going to be exactly the same in units of torr, because 1 torr equals 1 millimeter of mercury. All right, so that's another way that you could have done this if you caught that conversion early on. All right, wonderful. Last conversion here, we want to go from 1.75 atmosphere to units of Pascal. All right, that's our ultimate goal. Okay, let's remind ourselves of what that conversion is. We go back up here. All right, 1 atmosphere is equal to 101,325 pascals. Okay, so that's our conversion. We're going to put 1 atmosphere in the denominator so that the units cancel out, and then we'll put 101,325 pascals. Atmospheres cancel out. We're going to get our answer in units of Pascal, and if you plug it into a calculator, the answer is 1.77 times 10 to the power 5 pascals. And there we have it. We did a couple of conversions between different units of pressure. And with that, we can go ahead and move into our second objective on the gas laws. Now, to begin this section, I want to say that there are 4 variables that describe the physical state of any gas. Those variables are pressure, temperature, volume, and number of moles. Keeping that in mind, the first observation of the relationship between these variables was made by Boyle. And so with that, we're going to start with talking about Boyle's law. Boyle's law states that the pressure of a gas is inversely proportional to its volume. And that is when temperature and the number of moles of a gas are kept constant. This means if the volume of a gas is reduced, then the pressure increases. And if the volume increases, then the pressure decreases. So there is an inverse relationship between these two variables. And this relationship is represented as a hyperbolic curve in a pressure versus volume graph. Now, mathematically, we can write a very important expression, and that is P1V1 equals P2V2, indicating that the product of the initial pressure and the initial volume is equal to the product of the final pressure and the final volume after some change. Again, provided that temperature and moles remain constant. Then we can talk also about Charles' law. Charles' law explains that the volume of a gas is directly proportional to its absolute temperature. Here, provided that pressure and number of moles of gas are kept constant. All right, so volume and temperature are related. And that means if the temperature measured in Kelvin increases, you betcha, so does volume. And vice versa. If volume increases, then temperature measured in Kelvin also increases. Now, this law, it suggests a straight line relationship between these two variables on a volume versus temperature plot. This is when temperature is measured in Kelvin. Now, Charles' research also led to the understanding that minus 273.15 degrees Celsius corresponds to 0 Kelvin. This is the basis for the Kelvin scale, also known as absolute temperature. Now, for this law, we can also write a really important formulation, and that is that V1 over T1 is equal to V2 over T2. And this indicates that the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature after some change, provided that pressure and moles stay constant. Wonderful. So that's Boyle's law and Charles' law. Let's now talk about Avogadro's law. Avogadro's law states that the volume of a gas is directly proportional to the number of moles when temperature and pressure are held constant. And so what does that mean? That means that if number of moles increases, then the volume increases proportionally. And vice versa. If volume increases, number of moles of gas increases. And this linear relationship can be plotted as a straight line on a graph of volume, of moles of gas versus volume. Now, we can write an important mathematical expression for this law as well. V1 over N1 equals V2 over N2. So that means that the initial volume divided by the initial number of moles is equal to the final volume divided by the final number of moles after a change. Here, provided that temperature and pressure are held constant. Now last, but certainly not least, we have Gay-Lussac's law. This law states that the pressure of a gas is directly proportional to its absolute temperature. I want to remind you that when we say absolute temperature, we're talking about the Kelvin scale. And this is true when the volume and the number of moles remains constant. So this implies that an increase in temperature will result in a proportional increase in pressure, and vice versa. Increasing pressure will also increase temperature. Now, on a pressure versus temperature graph, you see a straight line affirming the direct relationship between these two variables. And again, we can write a really important formulation here saying that P1 over T1 equals P2 over T2, and this indicates that initial pressure over initial temperature equals final pressure divided by final temperature after some change. Again, when volume and moles are held constant. Wonderful. So those are our 4 simple gas laws. And this background information is going to help us segue into the ideal gas law and its applications. Now, to get our ideal gas law expression, we're going to start with taking 3 of our simple gas laws. We're going to take Boyle's, Charles, and Avogadro's. And what we're going to do now is express those relationships in a way that shows the relationship between volume on one side, all right, and pressure, temperature, and number of moles on the other side. So we know that for Boyle's law, volume and pressure are inversely related, so we can write that volume is equal to 1 over P. And what we have here is just a proportionality constant. Same goes for Charles' law. Volume and temperature are directly related, so we can write that volume equals temperature. And here we've just added, again, a proportionality constant. And for Avogadro's law, volume and number of moles are directly related, so we can write that volume equals numbers of mole, and here we have a proportionality constant. Now, what we can do now that we've written that is combine these relationships to write one expression. We can write volume on one side, and then we can write moles times temperature over pressure. And we can write it this way because volume is directly related to moles and temperature and inversely related to pressure. What we also have written is these combined proportionality constants. Since A, B, and C are constants, their product is also a constant, which we call R. This is the ideal gas constant. And R is actually equal to something. It's equal to 0.08206 liters times atmospheres over moles times Kelvin. All right. Now, what we can do is rearrange some of these variables. We're going to move P over and write PV is equal to nRT. This is our ideal gas law. This equation is called the ideal gas law. If you know any 3 of the 4 variables, pressure, volume, moles, and temperature, you can use the ideal gas law to determine the 4th. Now, something to note, you should always be careful to use the units for pressure, volume, moles, and temperature that are consistent with the units of the ideal gas constant. Pressure should be in atmosphere, volume should be in liters, number of moles is in number of moles, and T, temperature, is in Kelvin. Now, later on, we're going to be introduced to the ideal gas law in different units as well. For now, we're going to stick to this. All right, this is what we need to know. Now, I also want to talk about these conclusions a little more. The ideal gas law is an equation of state for a gas, where the state of the gas is its condition at a given time. A particular state of a gas is described by its pressure, volume, temperature, and number of moles. And again, Knowledge of any three of these properties is enough to completely define the state of a gas, since the fourth property can then be determined from the equation for the ideal gas law. It's also important to recognize that the ideal gas law is an empirical equation. It is based on experimental measurements of the properties of gases. A gas that obeys this equation is said to behave ideally. Now, this ideal gas equation is really best regarded as a limiting law. It expresses behavior that real gases may approach at low pressures and high temperatures. What does that mean? That means an ideal gas is really just a hypothetical substance. However, sometimes real gases do obey the ideal gas law and the ideal gas equation under specific conditions. What are those conditions? Low pressures, high temperatures. And actually, the ideal gas equation, all right, most gases obey the ideal gas equation closely enough at pressures below 1 atmosphere that only minimal error results from assuming ideal behavior. Now, unless you are given information to the contrary, you should assume ideal gas behavior when we're solving problems involving gases in this lecture. All right, so let's move on and let's say that we have a gas that is in one state. We're going to call that state 1, all right? And this gas in state 1 has the following variables to define it. It has pressure 1, P1, volume 1, V1. Those are the variables that describe it. It has number of moles, N1, and it has a temperature, T1. All right. Now let's say that over time, the state 1 evolves. It goes from this initial state 1, it evolves, and it ends up in state 2. All right, it evolves into state 2. And state 2, we can describe it with pressure P2, volume V2, number of moles N2, and temperature T2. Okay, we can relate these states mathematically. How? Well, we can rewrite the ideal gas law for each state to equal to the gas constant R. So we can shift things around so that we have an expression for state 1 that equals R. We're going to move N1 to this side. We're going to move T1 to this side. When we do this, we get that R equals P1 V1 over N1 T1. And we're going to do the same exact thing for state 2. We're going to move N2 over to this side and T2 over to this side so that we have R equals P2 V2 over N2 T2. We have both of these expressions equal to R, so these are equal to each other. And now what we can write is called the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. And this is going to be useful if we're given, all right, the evolution of two states and we need to figure out some variables. All right, and we're going to see that in some example problems. This is going to be really important. So now we have two important expressions. We have the ideal gas law, PV equals nRT, and we have the combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, we want to get one more useful equation, all right? We want to cover how to rewrite the ideal gas law using molar mass and density. We want to derive an equation where we can write the ideal gas law in terms of molar mass and density. So here is how this goes. We know that molar mass is mass per mole. Now I'm going to shorten molar mass as an M, and I'm going to give it little serifs here because we don't want to confuse this with molarity. What we can do now is shift variables around so that we can write something that says moles equals, all right? If we shift things around, we can write that moles equals mass divided by molar mass. And this is really good because we have the variable moles in our ideal gas law. So we could take our ideal gas law, PV equals nRT, and replace N with mass per molar mass. And what we get is that PV equals mass over molar mass multiplied by RT. Now, something else that we can do here is we can move molar mass over to the other side so that we have an expression that says molar mass equals something. If we move molar mass to the other side and then we take PV and we move it here, we can write that molar mass is equal to mass times R times T over V multiplied by P. And something really cool emerges here. Mass over volume. This is the definition of density. We can go ahead and replace mass over volume with density. And now we have an expression that says molar mass equals density multiplied by the ideal gas constant multiplied by temperature divided by pressure. Okay, so now we have three important formulations that we have talked about: ideal gas law, combined gas law, and then the ideal gas law in terms of molar mass and density. Now, what we're going to do is discuss how to tackle problems, rules for problems, before we start to tackle a couple together. The rules is this: if a problem describes a gas under a certain set of conditions, then you will use the ideal gas law. Keep in mind that there are 4 properties of a gas that completely describe the state of that gas. Those are P, V, N, and T. One way or another, you're going to be given 3 of the 4 variables and asked to determine the 4th variable. On the other hand, if the conditions of a gas change from state 1 to state 2, then you should use the combined gas law. And always be sure to use the appropriate units when solving gas problems. Temperature must always be in units of Kelvin. With that out of the way, let's go ahead and tackle our first problem together. This problem says a scuba diver has a compressed air tank with a volume of 8 liters. If the pressure of the gas inside the tank is 140 atmospheres at 20 degrees Celsius, what volume would that amount of gas occupy at 1 atmosphere and 25 degrees Celsius? All right, first we have to consider which gas law should be used. If a gas undergoes changes in condition, we just said that the combined gas law usually serves as the best approach, right? And our gas seems to change conditions here. And so what we're going to write is we're going to write our combined gas law and try to figure this out together. All right, our combined gas law, P1 V1 over N1, T1 equals P2 V2 over N2 T2. All right, then we're going to try to summarize the information that we're given. All right, so for state 1, what information do we have? What we have is that we have our initial pressure of 140 atmosphere. All right, we have our initial volume, 8 liters. All right, we have our T1, which is 20 degrees Celsius, but we want that in Kelvin. So 20 plus 273 is 293 Kelvin. And N1 is not given, all right? It's not given, but it is the same as N2, all right? Because it didn't tell us that moles of gas changed. So we don't know what N1 is equal to, but N1 is equal to N2, okay? Now let's write what we know about state 2, all right? State number 2. What are we given here? We're given that we have a P2 of 1 atmosphere, all right? We don't know what V2 is, all right? And T2 is 25 degrees Celsius, so we're going to try to convert that to Kelvin. 25 plus 273 is 298 Kelvin. And then again, we're not given N2, but N2 is equal to N1. So then if we're looking at our combined gas law, if N1 equals N2, we can go ahead and eliminate them on both sides. All right, we can eliminate it on both sides. Now what we have is P1V1 over T1 is equal to P2V2 over T2. And what are we trying to figure out? We're trying to figure out what volume, all right? What volume would that amount of gas occupy at 1 atmosphere and 25 degrees Celsius? That means what volume would it occupy after it evolves, the state evolves. So we're trying to figure out V2. So our goal then is let's rearrange things in our combined gas law so that we are solving for V2. If we move things around to solve for V2, all we need to do is move P2 over T2 to the other side. So we can multiply both sides by T2 over P2, all right? And what we have now is that V2 is equal to P1 V1 over T1 multiplied by T2 over P2. All right, that is what we need to set up. So let's do it now that we have all our variables. Okay, let's just write in our units. All right, P1 is 140 atmosphere. V1 is 8 liters. T1 is 293 Kelvin. All right, T2 is 298 Kelvin, and then P2 is 1 atmosphere. If we plug this into the calculator, what we're going to get for V2 is that it is equal to 1139 liters. All right, so V2 is equal to 1,139 liters. Okay, wonderful. So we went ahead and we solved this problem using the combined gas law. Let's do this next problem. All right, a gas cylinder containing nitrogen has a volume of 43.8 liters and a pressure of 1.51 times 10 to the fourth power kilopascals at 25 degrees Celsius. What mass of nitrogen is contained in the cylinder? The first thing we need to consider is which gas law should be used. Now we're given 3 of the 4 variables that we would see in the ideal gas law. We're given volume, pressure, and temperature. So we're just going to use the ideal gas law, PV equals nRT. Now the problem is asking us for mass of nitrogen, all right, which means that initially we want to solve for moles and then just convert that to mass. Okay, let's first start with writing down all the things that were known, that were given to us in this problem, converting them into their right units. All right, we're given that pressure is equal to 1.51 times 10 to the 4 kilopascals. We need this in units of atmosphere. Remember, because our ideal gas constant has units of atmosphere. All right, so we're just gonna convert this to atmosphere. What is the conversion? 1 atmosphere is equal to 101.325 kilopascal. We write 1.1325 kilopascals in the denominator so that our units cancel out. And then we write 1 atmosphere in the numerator. All right, this in the denominator, this in the numerator. Kilopascals cancel out. We're going to get our final answer in units of atmosphere. If we plug this into a calculator, we get 149 atmospheres. Okay, volume is given to us as 43.8 liters. Great, that's in perfect units. Temperature is given to us in degrees Celsius. We need this in Kelvin. So we're going to add plus 273 to convert Celsius into Kelvin. This is equal to 298 Kelvin. Wonderful. Now we have all the information. We're going to rewrite our ideal gas law to solve for N. We're just going to divide RT by both sides. We're going to divide both sides by RT. All right. And what we get is N is equal to PV over RT. Okay, now I'm going to erase some of this stuff here, all right? And we're going to start solving this. N equals, pressure is 149 atmosphere, volume is 43.8 liters, divided by gas constant, which is 0.0820, sorry about that, 0.08206 liters times atmosphere over moles times Kelvin, all right? And then temperature is 298 Kelvin, all right? I'm going to do some erasing here. If we plug this into a calculator, what we're going to get for moles is 267 moles. That is the number of moles. Beautiful. Now, our last and final step is to convert moles of nitrogen to grams of nitrogen. How do we do this? All right, we just use molar mass. Now, when they say nitrogen here, all right, nitrogen gas, I want us to be very careful here. Nitrogen gas is diatomic. We're talking about N2. All right, so what we're going to do is we're going to use molar mass to convert. 1 mole of N2 is 28 grams of N2. And this is going to give us 7.48 times 10 to the power 3 grams of N2. And there we have it. We solved the problem. All right, now this next problem says 55 grams of a certain gas occupies 10 liters under STP conditions. What is the molar mass of the gas? Now we're about to talk about STP, and this should stay STP. All right, I'm gonna define it really quickly for the problem, and then we're gonna talk about it again. STP stands for standard temperature and pressure. What is standard temperature and standard pressure? Standard pressure means 1 atmosphere. Standard temperature means 273 Kelvin. All right. So when problems say STP, they're giving you information about both temperature and pressure. And it is always pressure is equal to 1 atmosphere. Temperature is always equal to 273 Kelvin. Now, also in the problem, we're given liters. All right, we're given liters and we're given mass. This is really interesting, and we're asked to figure out molar mass of the gas. So what we're going to use is our ideal gas law that uses molar mass and density. Molar mass is equal to density times R times T over P. And we're given all of the information. Density, we're not given density directly, but density is mass over volume. And mass is 55 grams, and volume is 10 liters. So we can just go ahead and plug this into that term. We can write molar mass is equal to density, which is 55 grams over 10 liters, multiplied by our gas constant, which is 0.08206 liters times atmosphere over moles times Kelvin, multiplied by temperature, 273 Kelvin, over 1 atmosphere. Plug this into a calculator, we get 123 grams per mole. There it is, our molar mass for this gas. With that, we can go ahead and move into objective 4, all about gas stoichiometry. Here, we're going to revisit Avogadro's law, and there are 2 important consequences of Avogadro's law. First, when solving gas stoichiometry problems, if all of the gases are measured at the same temperature and pressure, instead of using mole-to-mole ratio, we can use liter-to-liter ratios. The second important consequence of Avogadro's law is that the molar volume of any gas at STP, standard temperature and pressure, all right, and standard temperature and pressure again means that pressure is 1 atmosphere, temperature is 273.15 Kelvin, or 273 Kelvin sometimes we'll round down to use in problems. All right, that means that the molar volume of any gas at STP is 22.4 liters. Now, in addition to other stoichiometry tips we've learned, like mole-to-mole ratios, these tips are going to help us solve different kinds of problems. And we're just going to go ahead and jump into one to make sure that we understand this. So this problem says, consider the first step in the industrial production of nitric acid. We have 4 NH3, 4 ammonias, plus 5 oxygen gas, gives us 4 NO plus 6 waters. What volume of NO gas measured at 1 atmosphere and 1,000 degrees Celsius could be produced from 10 liters of ammonia and excess oxygen measured at the same temperature and pressure? So we are given the volume of ammonia. We're asked to determine the volume of NO. The key point to see in this problem is that both gases are measured at the same temperature and pressure. Avogadro's law states that the volume of a gas is directly proportional to the number of moles when the temperature and pressure are held constant. And an important consequence of this law is that when two gases in a stoichiometry problem are measured at the same temperature and pressure, the stoichiometry problem can be solved just using liter-to-liter ratios instead of mole-to-mole ratios. So if we are trying to figure out the liters of NO gas, we can start by writing that we have 10 liters of ammonia, all right, and then using a liter-to-liter ratio, all right, 4 liters of ammonia to 4 liters of NO, all right? And what we get is 10 liters of NO. The liter-to-liter ratio was just obtained from the coefficients, all right, straight from the coefficients of the balanced equation in the same way that mole-to-mole ratios were determined. Remember, you can use liter-to-liter ratios for gases, all right, but not solids or liquids. And also you can use liter-to-liter ratios when gases are measured only at the same temperature and pressure. Those are the important caveats of these points. All right, so if you're dealing with gas problems and the gas is measured at the same temperature and pressure, you can use liter-to-liter ratios instead of mole-to-mole, just like we did here. And then if the molar volume of any gas at the molar volume of any gas at STP is 22.4 liters. That's an important thing to keep in mind. Now for this lecture, we're going to end here. In the next video, we're going to start with objective 5, which is all about Dalton's law of partial pressures. I really hope that this video was helpful. Let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.